Dr. Scott Linneman is a member of the Western Washington University faculty in the Geology department. He's been at Western since 2000. His doctorate is from the University of Wyoming. His undergraduate work was done at Carleton College. His areas of expertise are in geomorphology, geoscience, and in teacher preparation. His subject today will be talking about the OSO tragedy, and could it be repeated here in our county, and if so, when and where? What are the implications for private property owners? What's the science? So, without further ado, how about a big round of applause for Dr. Scott Linneman.
So I want to thank you for this invitation. My father and grandfather were small business owners. My older brother is a small business owner. I don't know what happened to me. Yes, I kind of fell in love with studying the earth, and that's what I'm going to try to share a little bit about today, because this is a really terrible thing for our state to have to deal with. But it's important that we understand a little bit about why this happened. And so I have a little presentation here. I'm going to try to keep this to under 30 minutes, and then what I'll do is open it up for questions, and anything you'd like to ask about, talk about as far as our area around here, I'd be happy to entertain those questions. So I'm going to talk mostly, well, for the first 15 minutes or so, about what happened down above the Stillaguamish River in March. So that you have a sense of the geology behind what happened. So I'm going to try to bring about some understanding there. You've heard a lot about the human element of it, so I'm going to talk about the geologic element. I'm also going to talk about why we're spending so much time, and I think still a little bit of state dollars on educating geology majors up on the hill over there. We have right now more geology majors than we've ever had. Lots of students are interested in this, and I think I can make a good reason why our geology majors would be capable of helping prevent occurrences like this all across the state. This is a little quote that you've probably seen before. Will Durant said this: civilization exists by geological consent, subject to change without notice. And that's especially true where we live. I grew up in Illinois, central Illinois, where I took my daughter for a short trip last week, and she said, "Dad, we just drove 5 miles without turning." And when was the last time you drove in this county 5 miles without turning? So, where we live here, we are very much under the constraints that the geology of the local area puts on us. And then finally, I'm going to try to make this point that the geologist's skills are particularly important these days. And we don't often think about what geologists bring, but I think we have this understanding in 4 dimensions. That is, we think about things in 3 dimensions, not we're able to project what's underneath the earth, but we also think in terms of time and how things change over time. We also are able to deal with the physics of most situations, and to understand really complicated systems with multiple causes. We don't do very many simple experiments with the planet that we have. Okay, so let's talk a little bit about what happened on March 22nd. You've, of course, seen this picture many times. The location, as you remember, is right here on the Stillaguamish River. We're up here. And I'll be showing some more of these kind of maps. Now, what you'll notice that on these maps is that there aren't any trees. It's not like a satellite photo. This is an image of the surface of the earth in which all the vegetation has been stripped off so that we can see what the ground is like. And I'll be showing you more and more of these kind of images. Okay, so here's your first test. You didn't know that you were going to be tested today. I thought this was like a class because nobody sat in the front. So when you look at this is a satellite image of the Stillaguamish River. And you look at the forest, and I ask you, so how many landslides do you see here? Well, You look at it a little bit, and you think, well, there's some ground showing over here, some bare ground. So maybe there's a landslide over here. All right, well, there's another way we look at the Earth, and that is by looking at topographical maps. And you maybe remember looking at these when you were hiking or fishing, and the topographical map of this area looks like this. So again, here's the Stillaguamish River, and you can see all these squiggly lines which represent the height of the land in various positions. And again, I ask you, how many landslides do you see here? Well, it's kind of hard to tell what might be a landslide here. But this is the data that most geologists had to work with until about 20 years ago. Now we can turn that topographic map into a model, and sort of like if you were making a clay model. And now this is that same topographic data, what we call a 10 meter, that is about 33 feet. And we can see, well, there's some kind of steep slopes over here, and there's some steep slopes over here, but it's kind of hard to pick out where an active landslide might be. And next I'm going to show you what we have now to work with. And this is, well, I'll preview it for you. So this is what we had until about 20 years ago. Now what we do is fly an airplane that has a laser system on it, and that laser system shoots pulses of laser light down to the ground. Some of that is hit by the vegetation. Some of it makes it all the way through to the ground. Much of it reflects back up to the airplane, where a detector knows how long that pulse took to come down and come back. And that now gives us a very, very good idea of what the shape of the Earth's surface is like. And that is a system called LiDAR. It stands for light detection and ranging. It's basically surveying from an airplane really, really precisely. So now I'm going to show you the map that we have to work with now. There's the same area. So you see a little bit more detail. Now again, this has the trees removed, because all what we've done is we've said we don't want to look at any of those returns that came off the canopy of the trees. We just want to see the returns that came off the ground surface. And then we can use the computers to remove everything above that ground surface, and this is what the ground surface around the Stillaguamish River looks like. And so this is where the landslide of 22 March occurred, but we can also see a lot of other features in here. Coming off this side, coming off this side, coming over here. So now I'm going to show you a few more of those pictures, and I'm hoping I'm going to train your eye a little bit. And I don't think it'll take seeing very many of these to start to get the idea. So here's that same image, and what we've done is zoomed in a little bit so that we can pay attention to this area right here. So if you're trying to tell where the landslide occurred, the river takes this big turn right up here. And there's a little straight line right there, and that actually is part of the story, because that was some revetment that was put in after 2006 slide. So here's a mapping of the landslides that a friend of mine at the U.S. Geological Survey did in the day after, looking at the same images that you just looked at. And so what he's done is mapped out by age all the different landslides, going from D being the oldest, C being the next oldest, B being younger still, and then A being the youngest. And what we see is that the landslide of March 22nd, which is in this Hatchard area, is really quite a bit smaller than this landslide, this prehistoric landslide that occurred over here. I'm going to say that again. What happened March 22nd, which has been described as unprecedented, never happened before, first of its kind ever, is quite a bit smaller than what had happened in the geologic past. And I taught you how to recognize that in 5 minutes. So I think we have the data now that's going to allow us to make some decisions about where people should and shouldn't be living on a long-term basis. And I think letting people make their own minds up is a good idea. But they need to have this data to be able to make those decisions. So a little bit of the history. Yes?
Can you back up again? How far ago, what were the time frames of the different colors?
The rest of these are not dated.
Oh, okay.
We don't know the exact times. I have...
What's your best guess, though?
We've looked up that's a great question. So we've looked up some of the very first timber surveys that were done in the turn of the last century. And they were reporting tree sizes in this area right here. And it turns out that all of the really big cedars were off of the edge of this area. Now that doesn't tell us for sure that this has happened in the period of old growth, which would be about 400 years in this area, but it might be that young. But it's not been investigated. We don't have the dates. I'd say what's for sure in the post-glacial period, in the last 12,000 years, but I'm guessing that this B one here is probably in the last 3,000 years.
What's the timeline on the other A area?
That's a good question. I don't know that. Yeah. Presumably, here's my sense. We know that that's a young one because the highway goes across that, and WashDOT knows when there's an active landslide because it affects road surfaces and they have to spend money to repair it. So I'm guessing that that's in the category of active because they've had to repair the road there.
So the highway department put a road across the top of the landslide that's active?
Yes.
Okay, thank you.
Yes. There are quite a number of places in the state where there's a highway that goes over active landslides.
The government is here to serve, protect, and help.
Yeah, well, you know, if you said, where can I put a highway down this valley? And you didn't have this map yet. You know, a lot of our highways were placed before we even had the topographic. Okay, so a little bit of history. The Hazel landslide is what the OSO landslide was known before March. And it was actually pretty well known as a landslide. So here's the history that we knew about before March. Back in 1937, from some very early aerial photographs showed that the area had some active landslides that was impinging or pushing down into the river. In 1951, there was a mud flow reported in the media from a side channel that blocked the river, blocked the Stillaguamish temporarily. In 52, there was a large movement, big blocks, up to 70 feet high that came down. By 1967, there was a slump of a large block that also produced mud flows in the wintertime, moving the channel about 700 feet, moving the channel of the river about 700 feet. This is about the time that the platting of that Steelhead subdivision was taking place, between 52 and 67. So the landslide was known to be active during that time. And then 1988, there was another small event. The river is pushed a little bit further to the south. And then the next biggest one was in January of 2006. The slide blocked the river and the Corps of Engineers had to cut a new channel. After this happened, there was still an expansion of the Steelhead subdivision that was going on. In fact, when this landslide was still moving in 2006, you could hear two things going on. You could hear the trees cracking as the landslide was moving, and you could hear the nail guns pounding as the new houses were being built. So what happened on March 22nd? So briefly here, you've seen this in the media many times. There was an event that was large enough that it was recorded on seismic stations. So this was recorded on a seismic station that was not very far away, but it was recorded on a lot of different seismic stations. So this is ground shaking due to the first slide happening at 10:37 in the morning. And then there was another ground shaking that occurred 4 minutes later. As of right now, it's not very well understood what these two different events were. The first one was certainly the beginning of the really large event which devastated that community and blocked the river. It's not exactly clear what this second event was. So I'll show you some images and maybe you have some ideas. So I'll show you some before-after pictures here that are kind of useful. So again, we're looking at this area right up here, and you can tell that there was an active scarp there before. The subdivision, the Steelhead subdivision, is on this side of the river.
The retaining wall is right on the...
So there's a revetment that's on the north side of the river. I wouldn't really call it a retaining wall. It's a set of logs that were put in with the idea to try to prevent just this bottom part from moving. It had nothing to do with what was moving up here. And if anything, it maybe created a false sense of security. So I'm going to go back and forth here a few times. So this is using that same LiDAR technique to survey the land surface and have the trees removed. So that's after, and that's before. And that's after, and that's before. I'll do this a few times, and you can start to get an idea what was happening down at river level and also what was happening on the hillside above. Now the next picture is going to be an actual satellite picture, so you're going to see the color of the trees and all that. So this is if we add the actual picture on. And so you can see the community, the Steelhead Drive community was under here. The highway is totally buried underneath here. The river is blocked up at this point over here. And this is the image that you've seen many times. Now, what I'm going to do now, I'll show you a few more of these images, and then I'm going to talk a little bit about why this happened. And then we'll talk a little bit about Whatcom County.
Were there seismograph indicators on this prior to the slide actualization?
Nothing.
Thank you.
Nothing. And there was no indication of a earthquake that might have triggered this. It's happened on a nice day. It wasn't even raining. Okay, so again, here's some before-after pictures using that LiDAR technique. And here's the actual color aerial photograph put on top. All right, so this picture is kind of hard to look at sometimes because what we've done now is involve the human element. So the red dots are all residences. Okay. So now you have a pretty good sense. Yes, Barbara?
What happened to the river? Did it turn into like a big lake there?
Right, so at this point the river did turn into a lake back here until it reached a high enough level that it started breaking through. It broke through a new channel right, not actually very far away from where the old channel was. And then, I'm not sure of the details, but I think there may have been some efforts to enlarge that channel to allow more of the water out.
So those homes to the right there in that plane.
They're underwater.
Oops, yes. They're either underwater or under mud. And it was very muddy water, so probably both. Okay, so why did this happen? So in order to understand why this happened, we really have to go back in time a little bit because the stuff that moved was all related to the last glaciation. So I'm going to start with that. Here's a picture of the dear Pacific Northwest about 20,000 years ago. So at 20,000 years ago, there was this big ice sheet up in Canada that was advancing down into the Puget Sound area by way of these lobes of ice. And this long lobe here is known as the Puget Lobe, named after the Puget Sound. I was just over in eastern Washington, and they care about this lobe. That's what was controlling a lot of the floods that came across eastern Washington, was this lobe over here. But what we're talking about is this lobe, and what really, for this story, what's important is when this lobe of ice was filling the Puget Sound, most of the rivers that were coming out of the mountain areas to the east were blocked by that ice. And when they're blocked by that ice, they form lakes. And so when you have lakes coming up against the ice, we have a lot of deposition of sediment, and that's what was being deposited in all the major river valleys, whether it's the Nooksack, the Skagit, the Stillaguamish, all had similar sequences of sediment because the lobe was blocking the river drainages. So this is kind of what that looked like. Now that's with all the ice in there, and this is showing you where the edge of that ice was, and you can see that the ice would have been blocking most of these drainages. And when the ice was blocking the drainages, it was creating lakes, and those lakes were then collecting sediment. So you've driven up the beautiful Skagit Valley many times, and you've probably seen that there are some flat hills along the side of the Skagit Valley. Those are places that mark the depth of that sediment, hundreds of feet thick. And the modern rivers have then cut down into that sediment. So this is how geologists look at this. This is the geologic map produced by the Washington Department of Natural Resources geologists. And this is the area that we're talking about in Stillaguamish. I'll zoom in on that, and you can see this is the situation that was present at the Stillaguamish, and it turns out that it's present in Whatcom County as well. The problem about the Stillaguamish is that it was much, much thicker. So these are all this is looking in cross-section now, like cutting a cake in half. And we're looking at this sequence of sediments, lake bed sediments, till from the glaciers themselves, and then outwash or gravels that came over the top. And this layer cake of sediments are what was on the hill slope above the Stillaguamish River. And this is where so when rain falls up here, the rain soaks into the ground, saturates these sediments, and so I'm going to talk just for a minute about the kind of the underlying cause of why this happened. So this is what geologists see. In this one, anything in this color, yellow here, is mapped as landslide. So there was no doubt that we knew quite well that this area had a lot of landslides in advance. So here's, I think this is a pretty bright crowd. I'm going to take about 2 minutes and try to teach you why this happens. So typically what happens with these landslides is it has to do with the water, because we're not dealing with blocks of solid rock here. We're dealing with unconsolidated sediments. You might call it soils, but these are soils that were on the order of 700 feet thick. So it's gravels and muds. And what happens is, when we have these really rainy winters like we did this year, the water table rises. As the water table rises, it has an effect on the strength of these materials, and you develop a slide plane, and then this material, driven by gravity and its low strength, moves downhill. So if we zoom in on that, this is what we would do with the geology students. It basically comes down to a balance between the strength of the material and the downward forces that gravity is putting on it. So what happens when it gets wet is the situation changes. So what's holding these grains together is basically friction. There's nothing more than just the weight of the overlying material holding the grains together. And for the most part, those grains were happy to stay together until we had a winter like we did this year, which involved a lot of rain. I'll talk about how much we got in just a second. So what happens is when those grains become saturated, because now they're underneath the water table, they're more buoyant. And when they're more buoyant, the grip between the grains becomes less. And as the friction decreases, their strength goes down. And there's actually another force that is going on here. And that is, if the groundwater is moving from a high place to a low place, like from a ridge to the river, it flows along a line like this. And when it intersects this spot right here, it actually has a upward trajectory. It's moving upward. And when it's moving upward, it actually drags those grains and produces another force that gives it even lower strength. It even lowers the friction even more. And the result is that the material has a lower strength than the forces that are pushing down on it. So the hydrogeology, or the water rock material interaction, is really the key to understanding what's going on here. And it's complex, but the bottom line here is that it's difficult sometimes to really accurately characterize what's going on with the water in the subsurface, and because there's all sorts of irregularities that change on a fairly small scale. So it's difficult to say, I can make a model that will predict exactly how much rain it would take to make that hill slope slide. What we're better off doing is looking at the history of sliding in that area and using the history as a way to guide us towards what's going to happen in the future. So what happened in the winter we just had? This is a graph showing precipitation in inches over here, and this is the days going across here. This marks the slide, and what we have is just a period of heavy rain, and then sort of not much rain, and then steady rain, steady rain, steady rain, more rain, not much rain. There wasn't much rain going in the immediate week before this happened. We can see that right here. Each of these is the amount of precipitation in each event. There was a little bit of rain in the week before, but nothing like one of these big storms that had come through earlier. But what it was doing was just accumulating, accumulating, and accumulating. So that's kind of the story that happened at OSO. OSO attracted the attention of landslide geologists around the world. One of the best-known international landslide experts is this guy I know named Dave Petley, who's a Brit. And he looked at this situation, and within about a day, he came to this conclusion. He said, to his mind, that this was a foreseeable event. And as such, the disaster, that is the loss of property, loss of life, is a failure in hazard management. So let's talk a little bit about Whatcom County. So some of you may be in the real estate business, so you know what I mean by comps. So we're going to talk about, are there comparables here in Whatcom County? And I'll show you a few, I think 5 different possible comparable places. The first one is just near Deming. This is now the Nooksack River.
Mark Nelson's place?
I don't think he's the landowner there, but this is the Nugent's Corner Bridge. This is what we call the Deming Clay Banks. That's the kind of local name for it. And so if we looked at this area, it would look in one of those LiDAR images very, very similar to the situation at the Stillaguamish. We have glacial sediments, steep banks, a river cutting into the base of those banks. The difference is really important here in that these banks are only about 150 feet high and not 650 feet high. So the chance of a really long run out is much less. But we did, in fact, a few weeks before the OSO event, have a river blocking event here. And not very many people in Whatcom County know about this, but so here's one of those images, and so here's those same bluffs with the river cutting into it. In the early 2000s, this is where most of the erosion was going on. There were 3 homes that were condemned and lost there. Right now, this is where it's going on, and here's probably the place where it's going to go on in the future. So in February, we had this event where the river cutting at the base cut in. This is the upper part of this landslide. The landslide actually went across and blocked the river. So downstream from this landslide, for about a half an hour, there would have been fish flopping around because the river was blocked. Now, luckily, there's a big bar. I'll show you in the next picture. The next picture I'm going to show you is from right up on the top of this scarp, looking backwards, looking across the river. And what you'll be able to see is that there's a big gravel bar that the river flows over during high flows. And so the river was blocked back here, formed a little lake, and then was able to flow over that bar. And within about a week, the high flows were able to cut off the toe of the landslide deposit, and it was flowing again normally. But there are pieces of this landslide deposit on that side of the bar. So it did go across the river and block the river. So this is comp number 1, something very similar to OSO. There's not a subdivision over there. It's an important thing to realize. Here's another comp. It's quite a bit different situation, but you may have heard of this. This is the metropolis of Acme in the South Fork Valley. This is Jones Creek, which flows down through, or just north of Acme. Used to flow right over Acme because Acme is built on the fan made of sediment that's come out of the Jones Creek Valley. And Jones Creek has some very weak rock on its sides in the valley. And this red zone is a place where a landslide comes down and occasionally blocks off Jones Creek. So it blocks off Jones Creek. A lake will form upstream. The lake will get big enough that it flows over the top, cuts down that landslide dam, and produces a flood of mud and boulders that go down onto the fan. Now, we've documented this has happened probably 8 times in the last 10,000 years. So it's pretty common, and when that happens, most of this zone gets covered with rock and mud, sometimes to a depth of 10 feet. There's an elementary school right there. That's the Acme Elementary School. So Barbara well knows about this situation. The county is dealing with some proposals right now to build a rather sizable berm that would direct those flows to the north and toward the river. So there's comp number 2. Comp number 3 is one that, this is the landslide at Jones Creek, by the way. So you can, when you see trees that are all cattywampus like that, you know you're dealing with a landslide. Okay, so the next comp is another one that people in the county are somewhat familiar with, Barbara, I'm sure, because we've been dealing with this for a long time. This is the Swift Creek landslide on Sumas Mountain, where a large mass of very, very low strength material is flowing downhill. Yes, those are my students. Don't worry, they're safe. So the Swift Creek landslide is flowing downhill at a very slow rate of a few meters per year. So it's moving about a centimeter a day, but it's enough, because it's so large, it's dumping large amounts of sediment into this small creek. And that's the major headache for the county, is dealing with this large amount, 150,000 cubic yards of sediment a year coming down into the agricultural lands near Everson. So the fourth one I wanted to talk about, I'm sort of going up in scale here, from small to bigger to bigger. The fourth comp I want to talk about is, again, this is the South Fork Valley. This is what we call the Van Zandt Dike, which is just a mountain of Chuckanut sandstone. And what we have here is evidence of a very large landslide. And you can see it very clearly in this LiDAR data. This large landslide here coming off of the Van Zandt Dike undoubtedly blocked the river for a while. The river has since cut its way through. The dating of this landslide is a bit sketchy, but it's probably a few thousand years old. So maybe 3,000 years old. That's a pretty big one. It's all forested now. It's hard to tell that it's a landslide unless you drive by there and you see these car and garage-sized boulders of sandstone out in the river valley. So that's kind of a long run-out landslide that is a type that we need to keep our eye on. And then there's the Big Daddy, and that is, as you get closer to the higher mountains, the steeper mountains, the potential for really large landslides goes up. And so the place we're looking at here is Church Mountain above Glacier. And so outlined by this red line right here is the scarp of a large failure that happened about 2,800 years ago. And that produced a landslide deposit that ran all the way down here, all the way past Glacier. So that's a landslide deposit that goes 10 kilometers, 6 miles. Now it's because it had a lot of elevation to get it started and had a long way to go. Now these are very infrequent events, but it happened 2,800 years ago. We don't know if there was an earthquake that triggered it, but there may have been. What we do know is that this area does have earthquakes. We know very well that it has big earthquakes and that we're likely to have more big earthquakes. And so probably some of the landslides, especially these bigger ones that I'm talking about just now, are going to be associated with large earthquakes. But certainly the one down on the Stillaguamish was not. There was no earthquake that started that. There was just a really wet season. So in terms of implications, here's what I'd like to leave you with. When it comes to planning and regulation, we need to think about these geologic risks, and we need to consider something that's not in the current regulations, and that is how far these landslides run out. Not just whether a slope itself is unstable, because we knew the slope at OSO was unstable. Nobody was building houses on that slope. We knew that was unstable. It was marked as landslide. But what wasn't taken into consideration is just how far out those landslides can go. And that's one of the things that we will need to consider. And the other one is that this new information, these LiDAR maps, should be easily available to the public. So if someone is trying to make decisions about whether they were going to buy a vacation or retirement home on Steelhead Drive, that they would be able to easily call up and look at these maps. And that would, in some states, that's a very easy thing to do. There's a Google Maps kind of thing, and you can just look at any place where that kind of mapping has been done. In this state, it depends on what county you're in. In this county, it's not very easy. In other counties, they have a system where you can look that kind of thing up more easily. So I think the folks in the county planning department are now currently working on trying to get this information more easily viewable by the general public. So that's what I wanted to tell you about, and I am open to talking about any of the aspects of this or any other things you're concerned about. So let's start right here with...
Stand up and ask your question.
I live right across from Church Mountain.
Ah,
And
yes.
I've been there for a long time.
Yeah.
I know it's a very rocky mountain, and Gulf Oil did 3 years of core sampling on the face of the mountain. My understanding is a lot of that sediment has already shed off.
Right.
Once it has shed away, and you have rock, I'm not sure how great a repeat is. I noticed that in OSO, that you can still see a plateau of sediment, and it's the plateau of sediment that's falling.
It's still
And
available.
so once our sediments have dumped,
Right, so
is
what...
the risk equal? That's my question.
I would say-
I look at rock and I get up in the mountains quite often. Thanks.
Immediately, well, after an event like that, there will be some shedding of material right after. But 3,000 years later, I would say it's certainly safer now than it was before the event. So you're exactly right, especially when we're talking about a bedrock event like that. But it was, the material is now, that rock that you're talking about that's now exposed, is exposed to the elements that will help break it down. And it's now easier for water to get into cracks. So the same forces that made it unstable the first time are working again to make it unstable again. So it may not move again for 10,000 years. I think having geological assessments of that is the way to go. So it's already been done there. So yeah, your hand was up next.
I found your, something I didn't know was all about the shear ability there and what affects that in regards to the water levels. So is there any way to, drill down and leave some kind of a monitor in place that in these areas where you know that there's possibility of slides that will tell you when that water is at a certain stage that may make that more likely to happen? Or, I don't know what you do to test
I would say yes. The short answer is yes. And there weren't any monitoring wells at this location that would have said exactly where the water table was. But the answer is yes, that kind of thing could be done. What you do with that information is another story. Whether you say, well, look, the water level is where it was in 2014, therefore we should evacuate. I think that's a very difficult decision. But yes, we can monitor water table levels, saturation levels, overpressuring levels. It's just, it costs money to put that kind of thing in.
Has that ever been done?
Oh, in other locations, sure.
And has it had any measure of success?
Not as far as predicting an event happening. Yeah. Yes.
Who actually makes the LiDAR maps?
Okay.
Who actually makes them?
Different people depending on the ones we're looking at. So the whole region was mapped in 2006 by the U.S. Geological Survey. At that point, they were trying to cover as much ground as they could. And so they had very few points per area. So we call that a kind of a low resolution data set. The many areas since then have been mapped in much higher resolution. So for example, the size of this table, there would be 8 to 10 points on every square meter. And that would be a high resolution map. Those are usually done by private contractors, LiDAR mappers, that then turn over a product with a specific specifications for accuracy.
Yeah,
So
my point was to find out who actually does it. USGS might contract it to somebody to do it, but if it's USGS oversight or whatever, it's taxpayer funded and should be available.
Right.
Anyway.
In fact, every bit of this data is, well, all of it that's been done with taxpayer money is available. There's a consortium called the Puget Sound LiDAR Consortium. You just have to have the skills that a couple classes at Western would teach you how to do. It's not something that the average homeowner would be able to just look up, at least the way it is in this county. So I think that's changing rapidly. There are other private contracting that also make LiDAR maps in more detail. So, yes.
With temperature, I seem to recall that viscosity and gravity changes with temperature. So given that, it would seem that as the weather changes and warms, the gravity of the water and the viscosity would change, and you tend to see more of this in the summer. But
well, you're right that the viscosity of the water does change due to temperature, but it's at a very, very, very slight level. It's measurable, but it's very, very slight. So we can include that in our calculations, but it really wouldn't have changed this at all. So, and plus, the water in the ground changes temperature only very slightly compared to the surface temperatures that we're experiencing. So yeah, I have my students, when I do the hydrogeology class, I have my students make calculations of groundwater flow at colder waters, and so they see that there's a very, very minor effect due to temperature. But it has more to do with just the position of that groundwater table.
As a follow-up, there was some discussion about the fact that logging had occurred.
Right.
But logging seems to me that would have reduced, if the logs were taken off, that would have reduced to a minor degree the soil pressure.
Right.
So if they took the logs off, it would be less apt to have failed.
Right. So what you're talking about is the weight of the logs,
Yes.
weight of the trees being removed. The other side of the equation is that a forest intercepts a lot of the incoming rainwater, incoming precipitation. It doesn't even reach the ground. In fact, in some cases, in some of our mature forests, 2/3 of the rain that comes in doesn't even reach the ground. So it's not, it just doesn't get there to soak in. So I think the implication, I mean, we've studied lots of places that have been old growth, selectively cut, clear cut, and looked at the soil conditions in each of those places. Exactly same geology, and we know that the first 5 years after a cut, the effect is mostly from the fact that there's more water soaking in. The next 5 years after the cut, it's because the root strength of those big trees is starting to decay. So the roots of the trees actually hold the soil together a lot. There's a lot of strength added to that material, the upper few meters of that material, just from the roots. But this was a deep landslide. It went way deeper than the root level. In the back there.
Is there any similarities to what happened on the west side of Whidbey Island and the soil conditions of this particular landslide? Because when I saw photos of this and then looked back at the Whidbey Island incident, it almost looked like the soil conditions were exactly the same. And I guess I'm thinking that eventually Whidbey will just fall into Puget Sound.
The conditions were remarkably similar. The geologic units were all glacial units at the Whidbey slide. It was a place that has had landsliding in the past. The lower subdivision there was in fact built on the landslide deposit, so it was as if you built a little subdivision right there. And the house that moved 100 feet or whatever was one of those houses. This is the Whidbey house. It was on top. So the start would be comparable to what's right there. So you're exactly right. There are a lot of similarities. Instead of the base being cut by the river, the base is being cut by waves. But otherwise, it's similar. So I don't think it's accurate to say well, certainly not accurate to say all of Whitby is going to move in, but the bluff areas are vulnerable in the long run. And we knew that that stretch was about a 3-kilometer stretch, has had a series of landslides, one after the other. And it's just really lucky that nobody was hurt in
Was
that.
it the water saturation?
It was water saturation. And what it was doing was going down and hitting a clay layer, a very impermeable clay layer, and increasing the pressure above that, the water pressure above that, right next to you.
You were talking about soils, so we have different types of soils within these landslide predictable areas. So are you seeing a real definite, that it's sliding where two different types of soils are coming together?
Ooh, she knows what she's talking about. So I'm going to go back to that. So I'm going to go. So we have to be careful what we mean by soil. Now, the master gardener refers to just that top foot of the roots are working in as soil. Here I'm talking about 150 feet of unconsolidated material that an engineer would call soil. Geologists wouldn't call this soil. We only call what's right at the top soil. But in fact, what you're saying is exactly true. The slide that happened in February that blocked the Nooksack initiated, well, you can kind of see, well, if you have good eyes, there's a layer that runs right across here, all the way across here. And that's a layer that we call the Nooksack sand. And we normally would think of a sand as something as a place where the water could flow freely through. But it turns out that the Nooksack sand has a layer on top of it about that thick that's a really tight clay. And so what happened was all that rain we were getting was soaking down in, it was going down in and hitting that clay and producing higher water pressures right above that clay, and that's the layer that slid. Yeah, good point. So all the way in the back?
Yeah. You came in 2000, you said?
Yes.
You know, we used to dredge our rivers up here.
Yes.
And, you know, the Nooksack, we haven't taken about over 30 million cubic yards out since we quit dredging. That has raised the water table. It raised the water table down there. In 1995, when it flooded in Wenatchee, it became an issue with the Speaker of the House. And he called a few of us together to meet with Ecology and Fisheries. Now, John Coster's farm backs on the Stillaquamish at Island Crossing. He made the statement that there's no fish in the river from June 1st to September 15th, and Ecology and Fisheries agree with that. And of course, then we said, then let's start dredging again and get the water table back where it's supposed to be, get the channels deeper so the water's cooler and the fish are healthier. And Fisheries said, no, we're not going to dredge. I put this whole thing on Governor Lowry, Christine Gregoire, Ecology, and Fisheries because they refused to let us get the channels back to where they wanted to go. If I take this napkin and stick it in this water, just the tip of it, tomorrow that whole napkin is going to be wet. Now if I throw sediment into that, it's going to raise that water level and it's going to get wetter faster. That's the cause of that slide. And we knew that in 1995 when John Coster, Cheryl Himes, and I walked out of the meeting because we wasted our time driving to Olympia.
The diagram I've shown here is like a cartoon. And what you're referring to is the height of the water table down here. And I think we could probably show with our computer models pretty carefully that changing this level by 10, well, how much? 10 feet? 10 feet of dredging is not going to have much effect over here. We won't even feel it over here. So it's hard to say what happens down here is what's controlling what's going on up there. But that's not research I've done directly. Now
we didn't have levees when I moved to Ferndale. Now we've got levees.
Yeah.
The river's wider, and we've got these big levees. Now we plant trees to keep the water cooler so the salmon are healthier, rather than keeping the channels deep and cold for healthy fish.
Okay. So one back here, and then Barbara.
You mentioned the seismograph data and the 4-minute separation between two events.
Right.
And two hydrogeologists that I know have discussed this, and they differ about what happened. And I wondered what your theory is about the two-part nature of the event.
That's an excellent question. And I've argued about this in a few different settings. So again, here's what he's referring to. The first large event, which matches the eyewitness account of material coming across, and then 4 minutes later, another event that the seismograph recorded. So my best guess is that what we're seeing in the second event is another flake that came off the top. That was maybe another 20 feet of horizontal thickness that had trees on it that came down and landed on the top of the material. And if you go to this picture, you can see right here, there's this area of trees that are just laid down, perfectly laid down. And that was my guess, is that second event is this landing on top of the first event. But I've heard people argue just as convincingly that that it was something off the side here. So it's a great question. I don't think it's resolved yet.
Could that be due to the top failing first on the saturated, get that slide going, and you get the gravity movement, then you get a second slide caused by that additional weight lower down?
Well, that is the other point of view, and that the initial failure was up here, overweighting the old landslide material, because remember, this was landslide material from 2006, just sitting there, so that this material came down, overweighted what was sitting there, and basically liquefied it instantaneously. Because if it was
4 minutes seems like a long time.
4 minutes does seem like a long time, but that is the best explanation for a single event. It doesn't explain very well a second event. But what we do know is that this particular situation is relatively unusual because all that material liquefied, and that's what was so dangerous, and that's why it had such a long run out. Now, we know now that that's a common event around here. If you just look off to the side, there's evidence that this has happened almost identically in the past. Yes?
Are any of these, you said these are, they're glacially deposited.
Glacial deposits.
But they're not glacially consolidated.
Some of them have been overrun. Some of the lower units have been overrun by the glacier, but most of the upper ones are not glacially consolidated. They did not have the weight of the ice on top of them.
Right, well, have any of them been tested to see if they're thixotropic?
That's a good question. So,
because that sounds like some of the thixotropic stuff up in Alaska, houses and great big developments and all that, and the earthquake comes and it just turns to slop.
So this is material that is basically made of clays in which the grains, the microscopic grains of clay are just like a house of cards with water in between them. And if you start to shake a house of cards with water in between, they'll lay down. And when they lay down, it loses all its strength. And so this thixotropic materials are blamed on what happened at Turnagain Heights at Anchorage in the '64 earthquake. I've not heard that explanation for these because there are some lake beds here, and it's possible that the lake beds behave that way because they're very clay rich. That's an interesting question. Barbara, sorry.
That's okay. Is there any comparison with what happens on Chuckanut?
Okay. So what happens on Chuckanut, when Chuckanut Drive is blocked, is that large blocks of bedrock. So probably the example, the comp that I showed that's most similar to Chuckanut Drive is not the clay banks, not Jones Creek, not Swift Creek, but this one here, where we have, if you look over here, the sandstone on the Van Zandt Dike and the sandstone in the Chuckanut Mountains is not sitting flat like a cake. It's sitting like a set of books that have been tilted sideways. And there are layers that have very low strength, and that would be like between the books. And what happens occasionally is those big blocks of sandstone sitting sideways, tilted down toward the bay, lose their strength and slide down onto the highway. And so what happens on Chuckanut Drive is probably very comparable to what happens here on a much, much smaller scale.
And then, so the Devil's Slide, when it's going to the west?
Yes, it came down off the mountain here, broke up into blocks and went across the South Fork Valley. Yes?
I have a little place on the North Fork, halfway between Deming and Kendall at mile marker 20. The mountain above me, is that moraine or soft gravel as you described here, or is that, because we have had slides in that area, Marshall Hill area. And so,
Oh, the Marshall Hill area.
yeah,
So
a
the,
couple miles above that.
yeah, so,
So that mountain, I'm asking.
that mountain is bedrock
That's what I thought.
with some glacial sediments on it.
How many
And
feet of glacial sediment?
depends on where you are.
So it could wipe out my neighbors across the road, but it won't wipe me out.
Unlikely, but we would, we would want to look at one of these LiDAR maps. And it would show us what the slopes are like in
Well, as
various
long as
locations.
it's about 10, 15 feet thick, is that the ground moraine on the top?
I'd have to look at the spot we were talking about with the map. So Gary's standing up, which is,
How about one last question?
okay. So there's one patient one way in the back who hasn't had a chance.
I want to go back out to Mark's house and then go a couple miles east. And if you look across the river, the mountain over there, there's an obvious east-facing scarp.
Yeah.
What do you know about that?
I know.
Well, I think the one we're talking about is very similar to this, and it has shed large landslides in the past. There was one shortly after I got here that went into Racehorse Creek. And it's a very, very comparable situation to that. So again, it's layers of this Chuckanut sandstone tilted up, sloping down, and there's some really, really weak beds in there. Some of them are thin little coal beds. A coal bed just a quarter of an inch thick has almost no strength. And so when water gets in there, or if a stream cuts away the base, those big blocks can slide. So fortunately, again, the Racehorse Creek slide, huge slide, but nobody was hurt.
I can't hear what you're saying. Anyway,
I was going to say, can Barbara speak to if they're doing anything, if they're just in like 30 seconds, if the county is doing to let us know what's happening?
But yes, and partly thanks to Scott and some other geologists. But the county planning staff is working on the kind of mapping that he spoke about. And we, I think it's going to determine a lot more in how permits are issued in the future, where they're issued. And I don't know, there's not going to be easy answers because there's already permitted places all over where there could be problems.
So you'll be notifying the people that are living in those areas?
You haven't got your notice yet?
Well, we did up in, where was that, in Glacier, that place that we actually bought out some of the houses.
Right, so at Glacier there was a place where there were two streams capable of flooding coming right coast. Then there's Glacier Springs where
It was in a
at Canyon Creek, another alluvial fan where some properties were bought out. So I think it just has to be done really judiciously. Highest risk first.
fabulous program. How about a big round of applause for that? Excellent. With that, we're adjourned. I'll look forward to seeing everybody in August.